I was looking at some news from the James Webb Space Telescope, and they were talking about exoplanets and how much work James Webb has done in the last 3 years. Because yes, James Webb's telescope has been in space for that long. So let's see. So here, let's look at a good definition. So first of all, exoplanets. An exoplanet is any planet beyond our solar system. Most of them orbit other stars, but some free-floating exoplanets called rogue planets are untethered to any stars. When I look at this, it may also be asteroids, because some asteroids can be pretty big. We've confirmed more than 5,800 exoplanets out of the billions that we believe exist. And the reason for that is, keep in mind that space is so big. We need to focus in one area at a time, and then we need to be able to see the hints that we've got an exoplanet. So let's see if we can look at some info. I was looking on the web, and I came across this thing right here. It is an unofficial James Webb Space Telescope exoplanet dashboard. So if you look here, what we've got, it has here more than 3,500 planets. No, total hours observed. There you go. We've got 127 planets. So these are the ones that we focused on. We've got some more planets indeed. The hours on transiting exoplanet. So here, keeping in mind that sometimes we are looking at something and oops, out of the blue, we see transiting exoplanets. And I'll share with you how we know that exoplanet exists. We also have gas giants that have been observed. We also have the Neptune-like, which are a bit smaller than gas giants. And then we have the rocky planets, similar to what we have in our solar system. So here, I do like this graph right here. It does change as we go along. So let's see if we can have a quick summary before I show you a large version. So first of all, you can see that from 2022 to 2025, we can see that we have observed a lot of transiting planets. Let's see if I can make it a bit bigger. Is it this one right here? There we go. So this is the same thing here. So we have here at the bottom the orbital periods. So here the orbital period for our planet is 365.25 days, and we have the planet mass. Now here we have 10 to the power of 0, which is our Earth orbital days, and you can see that many of the planets have a longer orbital period. Now, interestingly enough, you can see that here we have transit planets observed in blue, planned in green right here, and we already have information about the orange ones here. Keeping in mind that they're very tiny from our perspective, so we started with looking at larger ones, and now we're going to focus on smaller ones. Now, interestingly speaking, people will say, well, what are these tiny little gray dots right here? The gray dots are from a mission called Keppler. So Keppler was a telescope that was sent in 2009 into space. And for 9 years, it took pictures of space, and it was only looking to see, are there any exoplanets? So the purpose of the Keppler telescope is to see where exoplanets were, and the James Webb telescope is getting more information here. So let's see if we can look at another graph that was interesting here. So planet mass histogram. So that's interesting. So you can see that a few of the planets are like ours. We have many planets that are 10 times the mass of Earth. So here they call them like Neptune. And then we have the like 100 to almost 1,000 times the mass of Earth. Now you have to keep in mind that the bigger the mass, the more the gravity would be. So here the main purpose is to see, is there any living organisms somewhere else in the universe? Now the bigger the gravity, the harder it is for any organisms to be going through. So here's the example of what Keppler telescope looks like. So here it was launched in 2009 in search for exoplanet. So here the purpose was to have the telescope aim at one area and take pictures. That was the only reason why it was there. And Good. So originally positioned to stare continuously to about 15,000 stars. Now the question here is, why do we have to look at stars to know if we have exoplanets? And I'm going to talk about that in one moment. So here it is in 2018 when they retired the Keppler telescope. Now the reason why they retired it is that the fuel of the telescope ran out. So that means there was no way to redirect the telescope where they need them to be. So what happened? They shut it down in 2018, and that's why we know that we haven't received any data since that time. Good. So let's see how, we have, good. So this is an amazing picture. So here we have a graph, and it's a graph over time and brightness. So here is how we find exoplanets. So first of all, we have to look at stars. When you look at stars, you will see that there's a luminosity of that star. So here there's a brightness that is consistent this way. So that means that the planet is going in orbit around the star, it goes behind the star, and then at the front, or it could go the other way around. However, once that exoplanet is in between us watching and then the star, what happened here is that there's a decrease in brightness of this star. Now, if there's a decrease in brightness, it does not mean that it is an exoplanet. First of all, we need to take some time to see if we can figure out a predictable transition or a predictable orbit. So that means that at every given time, we have the same dip in brightness. This gives us a good idea that it is an exoplanet. Now, it does happen that sometimes we have a celestial object that just goes in front of that star and continue. We call them transiting exoplanet, and they could be either from other stars or it could be asteroids, but it's not what we call exoplanet. So the only way we can get an exoplanet is to be able to know that we have an object that is in orbit around that star. And the only reason is to see the decrease. Now, I do a lab in my astronomy class where we have, instead of a star, we have a lamp, apologize. And what happens here is that I have a distance of about 5 meters. And what happens is that we are using our phone and we have apps to record lux meters, which is the luminosity. And then we try to see how the luminosity is decreasing when we have an object going between the lamp and our phone. It's amazing. Depending on the size of the object, there is, so if it's a small object, it's a small dip in brightness. If it is a much larger object, then it's a much bigger dip in brightness. Ultimately, if you had something that was as big as that star, we could actually have what we call an eclipse. So this is quite exciting. So this is how we know if there is or not an exoplanet. So here's another example of reading. So this one here is for the exoplanet SGTP 32b. And here what we have, we can see the relative flux. So they're not straight line. What we have here, we have statistical information. So we have light coming from that star. And here we have, so here as you can see, we have the dots of the luminosity plus or minus the sources of error, because keep in mind that light is going through the universe. There might be dust that is changing some of the light rays, the same way that if you have a telescope, if you are on the planet here on Earth and you look at the star, you can see twinkling of the stars. And that's why space telescopes are amazing. So here, looking at the information we have here, we have a statistical brightness of the star. That is our baseline before and after the transitioning, or the transiting in front of that star. And then you could see there's a dip in luminosity once that exoplanet goes and starts to go in front of the star. And then here is a time when we have transiting in front of that star up until that exoplanet passes through. And then we have here a decrease in luminosity. So the same way that we have sometimes eclipse, solar eclipse on the planet, solar eclipse, there's a lot of the brightness going down. Here we have small exoplanets that is going through. And yes. So here's an example where we have our sun, and you can see here the sunspot. And here you could see Mercury coming in between us and the sun. See how small this is? Now, given size, it is an actual, we can actually, statistically speaking, see the decrease in, oh, there's a little 50-minute video. See, we have Mercury going in front here, crossing between us on Earth, the telescope, and the sun. And you could see here Mercury transiting in front of our star. And because Mercury is a planet in our solar system, it is reoccurring because we're on the same plane of orbiting, and we can see Mercury in transit. Isn't it amazing? So this is what we call, this is an example of how we could see a decrease in the quantity of light. Now, because Mercury is so small, the change of light is small. Let's see if I can do the same for Venus. That's a good one. This is, look at how beautiful this is. So this is a time lapse of Venus between us and the sun. As you can see here, Venus is much closer to us because its orbit is further away from the sun than Mercury. And you could see how this would create a decrease in quantity of light coming to us. So this is one way for us to know that Venus is a planet in our solar system. So the same way over the centuries, we figured out that Venus had a smaller orbital radius than Earth. We are doing the same thing with exoplanets. So it's always nice to see. Now, the next thing that is amazing is that what happens when you are using the James Webb telescope and then you're looking at those transiting stars, where we have, no, the transiting exoplanets. So let's say that we have a star right here, and we have an exoplanet with a defined path, a defined orbit. Now, what's interesting here is that the light of the sun, or that star, is going and is blocked by that planet. But if that planet here has an atmosphere, the light ray going through the atmosphere here brings us information about the atmosphere of the planet. So keeping in mind that I remember when, and there's a few videos a few weeks back, and I'm going to see if I can put here a card, or I put it at the end of the video, where we have sent a probe to see the composition of atmospheres of different planets and exoplanets, and it was confirmed that the Earth was a habitable planet. But here what happens is that we have here a change in wavelengths, and here's what we can see. So here we can see a change in wavelengths of the light when it goes through the atmosphere. So here the amount of light is let's say given. So here we can see that if there's a dip, some of the light is absorbed by oxygen molecules or ozone molecules. We can have some of the light that is absorbed by water. Here's two examples, and this one here. We also have here wavelengths that are absorbed by methane here and there, and here we have ozone as well. And then we can have here in green, in the red, carbon dioxide. So imagine if we can see a star and the light of that star, because we know by observing the star without the exoplanet, we have a signature of that star. What happens is that when the exoplanet is there, we can see the change in the wavelengths. And if you can realize that on that exoplanet, there is ozone that is protecting the ground from solar rays. We have oxygen, we have water, we have carbon dioxide and methane. Then people say, well, is it possible that it is an habitable planet? And if that's the case, is there any living organism there? So this is why it's so exciting when you think of looking at exoplanets and the information we get from them. And there we go. And that is the main topic I wanted to share with you today, where exoplanet is an amazing thing because we're discovering something new. And interestingly enough, if you look at the Kepler's data, the James Webb telescope data, and if you remember earlier today, I was showing you, let's see, where is it? Let's see, I lost it. I was showing you the data from the James Webb The data is available, but we need people to analyze the data. So AI will help us, amazingly speaking. But there's a lot of data to look into. And that's why a lot of people in astronomy, astrophysics might actually find information that scientists or professional scientists and astrophysicists might miss, given the sheer amount of available data. So this is the key point I wanted to share with you today. If you have any questions or clarification questions about exoplanets, please put them in the section below. I'm going to be more than happy to answer your question on this. Have an amazing week. And I will put here a link to another video about science, the one about that Earth is an habitable planet. I'll see you there.